In the last lecture and the problem example we saw, what we observed that when you take an element and if you rotate it about particular angle, your stresses change. Your sigma x, sigma y, tau xy becomes sigma x prime, sigma y prime, and the tau x prime y prime. What we are going to see now is that does there exist some particular angles of rotation for which your normal stresses become their respective maximum and minimum, and those angles of rotation and the planes about which they rotate, they are known as the principal planes. As you can see already written here, there's a principal planes, the principal directions. And does there exist another angle of rotation for which the shear becomes maximum? So let's go ahead and take a look at that. Now, as you have already seen, this is what we saw, that if we take an element like this over here and if you give a rotation, again we are dealing with the positive rotations here, theta over here, general positive. So for which you have these rotated about the rotated plane, you have this updated state of stresses that is there. So what we are trying to address is that does there exist an angle of rotation theta, that is, let's call that theta equals to theta p, at which the stresses sigma x prime and the sigma y prime reach their respective maximum and the minimum values respectively. Now this is important. Why does it happen that when one of them reach their maximum, the other one reaches the minimum value? Because remember that we have that relationship always value. So let's just quickly write that. We have the relationship that sigma x prime plus sigma y prime equals to sigma x plus sigma y. So that means that if one of them is reaching their maximum value, the other one must reach the minimum value to always keep the addition as a constant number that you initially started with, right? So this is important. So that is why when one of them reaches their maximum, the other one must reach the minimum value over here, right? So now the question is that how do we find this theta p, that rotation where one of them becomes the maximum and automatically the other one becomes the minimum over here? Well, the answer is very simple, and I know you are thinking about this already. For example, if I take this expression and if I differentiate this expression with respect to theta, I will get that particular angle at which my sigma x becomes a maximum and sigma y becomes a minimum, right? So we have to essentially do the differentiation. So if you take this expression and then you differentiate, so this step shows the differentiation that you have over here. These are very simple algebraic manipulations, so I'm avoiding writing it and doing every step. If you're interested, you take this expression, you differentiate it, you will get this one over here. Then if you equate this expression to 0, that will give you the theta, that will help you calculate the theta at which the maximum happens. And it turns out to be, the expression for theta boils down to something like this. So tan 2 theta p, and theta becomes equals to theta p because p, remember, p represents the principal direction. So let's maybe make a note of that. P means the principal direction, right? So in this principal direction, your sigma x is going to be maximum and automatically your sigma y becomes the minimum, or vice versa, depending upon the sign and everything, right? So this expression comes out to be a simple expression, something like, so this is the ratio of the shear in the original element tau xy divided by sigma x minus sigma y divided by 2. Now what does this mean? So this means that now since it is tangent of 2 theta p, that means there are two angles 2 theta p separated by 180 degrees, and the subscript p, as we wrote over here, it represents the principal direction. So about one of the theta p's you have the maximum stress, and about the other theta p you have the minimum stress sigma 2 that is occurring over here. So now you're replacing sigma x prime with the maximum stress sigma 1, sigma y prime with the minimum stress sigma 2 over here, which is separated by this that 2 theta, that is 180 degrees over here. Now since in this one you have this 2 theta p separated by 180 degrees, theta p, that is 2 theta p divided by 2, theta p must be separated by 90 degrees over here. So that is what is over here. So the actual angle of rotation theta p therefore rotates by 90 degrees. So let's take a look how that element looks like. So this is again the general description for that one. So what we have done is that similar to what we did before when we were just giving our arbitrary angular rotation theta, now I have rotated about a particular angle of theta p1 about the x-axis over here. Now since this is theta p1, the original faces were perpendicular to each other. This one rotates by an angle of theta p2, which is nothing but theta p1 plus 90 degrees. So this is what it is. So this is the angles are separated by this rotates by this 90 degree over here, because two theta p's are separated by 180 degrees. So if one of them are rotating by theta, so it's easy to keep a track of. If you know the rotation of one, so the other one must be the theta p2 must be equals to 90 degree plus theta p1 that you have over here, right? And also remember that these are the stresses. So sigma 1 is the maximum stress and this is the minimum. So now if you go back and if you substitute this tan to theta p2 in the general expressions, remember the general expressions for sigma x prime and sigma y prime, which we wrote out in the previous lecture. If you substitute in those general expressions, now remember for the principal direction, sigma x prime becomes equals to sigma 1, sigma y prime becomes equals to sigma 2, and this is the general expression that you have over here. So for sigma 1 you are going to use this positive sign, so the expression boils down to sigma x plus sigma y by 2. This is the first term of that transformation equations, remember, so that remains the same. And for the remaining term, it is essentially the square root of the sum of squares of the last two terms, that is sigma x minus sigma y2 square plus tau xy square. Now for sigma 1 you are going to use the positive sign because that is the maximum stress that you want to get. For sigma 2, which is the minimum stress, you are going to use the negative sign. And you see that your relationship is preserved. So at about any angle of rotation, if you want to write it, even here also you have sigma 1 plus sigma 2 is equals to, for any angle of rotation, sigma x prime plus sigma y prime, which is again equals to your sigma x plus sigma y. So that also always stays value. So if you add sigma 1 plus sigma 2, this term cancels out, so you end up with sigma x plus sigma y. Okay, and also this is the angle of rotation which we wrote in the previous page as well. So that is tau xy divided by sigma x minus sigma y divided by 2. So what it is, so these expressions give you the maximum and the minimum principal stresses, and since as I mentioned these are the places where the maximum happens over there, so these are the places where these are known as the principal planes. So these are the principal planes, essentially means the planes where you cut your element or where you cut within the structure where your stresses essentially peak up, your normal stresses reach up their maximum and the minimum values over there. Now let me point to you something that is very interesting. If you take a look, right, if you take down, now I want you to spot the difference over here. So this is the original element which we started with. We have not rotated it or anything. This is the original element we started with. Now for this element, when I gave a general angle of rotation theta, any angles, anti-clockwise angle theta which we are giving, this was a set of stresses about that rotated plane where we have the sigma x prime, sigma y prime, tau x prime, y prime about this angle of rotation theta. Now when I am rotating about theta equals to theta p, that is about the principal planes, you see this is the set of stresses that we have, that is sigma 1 is the maximum stress that you have, sigma 2 is the minimum, or vice versa, depends upon the sign and so on. So this is when it is rotated at theta equals to theta p. Now what I want you to observe is the difference between this and this over here. Do we have the normal stresses? Yes, we do have the normal stresses, but what happens to the shear? So the shear essentially vanishes, and if you go back and the tan to theta p that we calculated, if you go back and plug that in the tau xy equation, what you will observe is that when an element is rotated about the principal direction, your shear stresses essentially vanish. So this is a very important observation that you must keep in mind, that if you take an element and if you rotate it about the principal planes, your only normal stresses remain, and those normal stresses are the maxima and the minima, and the shear stresses vanish. So this is important, please remember this one. So tau x prime y prime about the principal planes, it vanishes, that is tau x prime y prime at theta p1 at theta p2, both about this face and this face is vanished. And it's easy to note, if the remember from complementarity, if your tau vanishes in one of the places, for all the across the 4 places it has to go. If it occurs in any one of the faces, it has to crop up in all the faces that you have over there, right? So in summary, 3 important things to remember. First of all, that about this theta p1, theta p2, you have the principal stresses. The stresses are known as the principal stresses. Why? Because your element is rotated about the principal directions. Also, this, how do we get this angle over here? We simply substitute this in this expression. You will get theta p1 90 degree plus theta p1 equals to theta p2. So this gives you a principal planes, and lastly your tau x prime y prime was 0 on the principal planes over here. Now with this, what did we get? We got that if you take an element and if you rotate about a particular angle theta p1, theta p2, you only have the principal stresses and no shear stresses. Now remember, the original element which we started with was something like this over here. And what we did to essentially get this one is that we just simply differentiated this particular expression. So this is the slide we saw a few slides back. We just differentiated and we got theta p. Now, is there, the second question that we have, that we're trying to address in this lecture, is that is there another angle of rotation where your tau xy about a particular rotated angle, is there any angle where your tau x prime y prime becomes the maximum values? We know that when rotated about the principal direction, tau x prime y prime vanishes. So is there any other angular rotation where the shear becomes a maximum value? The answer is yes. And how do we get that? How do we get that particular point? So the question again is that, is there an angular rotation theta s? Now I'm going to call this theta s. Remember theta p, where we were having the normal stresses reach their principal values or becoming principal stresses. Theta s is the angle where your tau x prime y prime reaches the maximum value. So how do I get that? The answer is simple again. I take this expression and I differentiate with respect to theta. I equate that to 0. So I get a value of theta s at which my shear stresses become maximum. Now, do you think that the plane where the shear stresses become maximum, the normal stresses disappear? Because in the principal plane we saw that where the normal stresses were becoming maximum, the taus were vanishing. So does it happen in the contrary way as well, that where your tau x prime y prime becomes maximum, does sigma 1 or sigma 2 or the sigma x prime and the sigma y prime vanish? Let's take a look. So it so happens that if you take this expression and you differentiate with respect to this one, you get something like this over. So this is the tan 2 theta s. The tan 2 theta s so this becomes 2 theta, since this is tangent, 2 theta s separated at 180 degree, where your shear stresses become the maximum over there, right? Now remember, shear is an element which is like if you have it on one particular face, all the other faces have equal values, modulus values, and the directions are automatically fixed by one of them. Now if you take this expression over here, now let's take a look at this expression. You see that previously for the principal directions we got this expression, and you compare this value with this one over here. What do we see here? What was the tau xy? It has gone below, and what was the denominator becomes the numerator over here, and this whole thing has a negative sign. So this expression is simply a negative reciprocal of this expression over here. And what does that mean? Remember your trigonometry. So it means that since it's a negative reciprocal, that means your theta s and theta p is separated by an angle of 45 degrees. It is such an interesting observation that you see over here. That essentially means that your plane of maximum shear is 45 degrees away from your principal plane. Again, let's take a few steps back. We had an original element. We took that element and rotated about a particular theta p, where we got the principal stresses. From that, if you deviate a further 45 degree, you will get the plane where you will have the maximum shear stress that is occurring. Now coming back to our original question, does the sigmas vanish? The answer is no. So although for this theta s rotation that you have over here, and here this rotation is shown about the clockwise direction, when we look at a problem, this will make much more sense to you, that you will see that at these rotations, at this theta s rotation, your tau x prime y prime becomes with the maximum tau max. So this is, if I just write it out, so this is essentially tau x prime y prime maximum, which is this guy over here, it becomes this expression. Remember, we have seen this expression previously in the principal stresses, that last element, that plus minus square root of sigma x minus sigma y by 2 square plus tau x y square. That's the only thing that remains when you calculate your maximum stresses. And it so happens that in these planes where we have this maximum stresses, your normal stresses do not vanish. Your normal stresses becomes equals to this average stress over here. You may average means sigma x plus sigma y by 2, which is the original stress in the original element, right? So at the planes of the maximum shear, the normal stresses still exist. Now you may remember these expressions from where, remember the chapter on torsion that we studied, where you had a pure shear element, we rotated about, we were giving twisting to the chalk and it was breaking, and at that 45-degree, remember, you had the tau as tau max and your sigmas was the sigma average, right? So this is essentially what you get over here. So in a nutshell, again, when you take the element and if you rotate it about that angle which gives you your maximum shear, at that position you will still have the normal stresses, and the value of the normal stresses across all the four faces, the directions will depend upon the directions of the stresses in the original element. So don't be bogged down by the directions. When we calculate that, you will see how they change, but the magnitude is going to be the average of the original stresses that you have, right? So to summarize this entire lecture, what we have over here is that your principal stresses represent the point of the maximum and the minimum stresses, that is sigma 1, sigma 2. When you have in the principal stresses, there will be no shear stresses, that is tau x prime y prime becomes equals to 0, right? Now when you have the element rotated at the angle where it gives you the maximum in plane shear stress, in that case your sigmas or the normal stresses do not vanish, but it becomes an average normal stress which also acts on the element. And lastly, that the plane for the maximum shear stress is oriented at 45 degrees away from the element which represents the principal stresses over here. So lots of different formulas, but hopefully easy to remember. Let's go ahead and solve a problem to see that for an element how we can get the planes for the maximum principal stresses, or the principal stresses as the maximum and the minimum, and the maximum in plane shear.